let's get started. Welcome to ENGG2500 crash course, or the fluid mechanics crash course. So I'm gonna quickly go over this because I forgot to record the last one. So I'm pretty much just gonna go through the topics of the course, and what I'm gonna mainly cover are gonna be like the first three. So fluid properties, hydrostatics, and continuity. Then there's also energy and momentum, which is another topic. And then these are the rest of the topics over here. So we've got pipe flow, which is the largest topic, dimension analysis, which is like the most mind-numbing one because it's just mainly a bit of math and a bunch of algebra. Physical models, which actually uses dimensional analysis, but it's pretty easy. And then these two pretty small boundary layers and drag force. They're pretty small topics as well. So first thing, I'm going to take a look at fluid properties, which is to do with the mass, weight, and density of a fluid, as well as the viscosity. Alright, then hydrostatics. Hydrostatics is pretty much just the, it just deals with pressure versus depth, and then forces. So pressure and forces to do with fluids. And then there's continuity, which I'll introduce you guys to fluxes and bucket hydraulics, and then energy and momentum. So there's an equation called the Bernoulli's equation that you guys will pretty much be using throughout the most of the course, I think. Yeah, most of the course at least. Right. Then you also, I won't go over these two over here, but there's also something called head loss and momentum. Okay, let's move on to fluid properties. So first thing first, from primary school, you guys should probably remember the three states of matter. So there's solids, liquids, and gas. So solids are just solids. The study of solids you do in a different course. However, in this course, we only care about liquids and gases. So I've got it over here. So fluids consist of liquids and gases. A liquid is just something that has no fixed shape, but does have a fixed volume. Gases have neither fixed shape or fixed volume. Alright, it's not too important. Just wanted to give you guys an introduction that we can also take a look at liquids as well as gases. Now, fluids have something called a density, which is the mass per unit volume, is given by the formula. Density, so this is our density, equals to mass divided by volume. So we call this letter rho, or we just call it density, right? But that's how you pronounce it, rho. So density is equal to mass over volume, and our units I've put in red over here. So kilograms per meter cubed. Now, an extension of density is something that we call unit weight. So we call this formula, this symbol, gamma, the unit weight. So the unit weight is the weight per unit volume, right? So weight per unit volume is going to be weight divided by volume. You can break down weight even further because W is equal to mg. So mg divided by v. And because we know that m divided by v is our density, we can just say that our unit weight is equal to rho times g. So it's pretty much just density multiplied by a factor of gravity, the unit weight. Alright, so there are some important values that I've put here as well. The density of water, which is 1000 kilograms per meter cubed and 1 gram per milliliter, as well as the unit weight for water, which is 9810 newtons per meter. So in this course, we use gravity as 9.81. Yeah, that's pretty much it. So you can see that to go from here to here, we just multiplied by 9.81. Okay, next thing I'm going to talk about really quickly is the relative density or specific gravity. So what specific gravity is pretty much just a way to relate the density of a fluid or unit weight of a fluid. You're trying to relate that to the unit weight of water or density of water. So specific gravity, so there's two symbols for it. There's this one, which we mainly use in fluids. This one you see in soils. So in this course, we're going to use SG. it's equal to the density of your fluid that you're analyzing. So the density of the fluid divided by the density of water. Right? Now there's an equivalent equation. The unit weight of the fluid divided by unit weight of water. So the reason for this, I'll do it over here. So the unit weight of a fluid divided by the unit weight of water is just going to be rho, the density of the fluid times G, over the density of water times G, and the G's just cancel out, so you get this, which is what we have over here. All right. And it's got no units, it's dimensionless, so you don't have to worry about units. An example of how you would use SG, so they might say SG is equal to 0.89. So the specific gravity of a certain fluid is 0.89, and in some pressure calculations you might need to find the unit weight of the fluid, right? So in this case, you know that the unit weight of a fluid divided by the unit weight of water is equal to SG. This is equal to SG, which is equal to 0.89. We already know what this value is because you can assume that it's 9,810, unless the question says otherwise. And so you can just be like, unit weight of the fluid is 0.89 times unit weight of water, which is 0.89 times 9,810. Then this equals to some value. Alright. So at first, the unit weight of the fluid is unknown, but then because they've given us a specific gravity, you can actually find out what it is. Next, the specific volume. This is not too important. Like, I haven't really seen any question ask about this, but it's pretty much just a reciprocal of your density. So specific volume, or Vs, is equal to volume over mass. The units are going to be reciprocated as well, so it's going to be meter cubed per kilogram. I don't think there's any use for this. It just exists. Okay, so I'm going to skip over it. Okay, next. Viscosity. So this is another fluid property. It is the resistance to flow. So whenever there's shear stress that's applied to a fluid, this results in the motion of the fluid. I'm pretty sure that's pretty self-explanatory. So if you apply a force onto a fluid, it's going to move. Right? So imagine you have a block of fluid, and from the side you're applying a force. Right? That fluid, after you apply the force, it will move with some velocity u. So this is some velocity u. Alright. And what also happens is that there's a shear stress that is induced within the fluid. So one way you can think about this shear stress is that the fluids, think of fluids first of all as layers, individual layers which stick together. So this is the whole fluid block, right? But you can break it down into different layers, right? And there'll be some sort of shear stress that's induced within. So there'll be some like shear stress here that's induced because the fluid is moving, right? So it's shearing between these layers. And that pretty much what it is. That's our viscosity. So the resistance to flow. I'll quickly talk about this formula over here. This is a formula that you see in solid mechanics, ENGG2500, but it's pretty much just our shear stress, which is equal to force divided by area. But our area is something that we call the shear area. It varies from case to case, so I'm not going to cover it too much right now. I'm going to go over all the cases first, then I'll talk about the cases individually. And the F is just the applied force. Okay, we're gonna need this when we're talking about the law of viscosity, which is right here. So this is what we call the law of viscosity. So after you apply the force, we know that it's going to be moving with some velocity u, right? So we can relate the velocity, the shear stress, the force, the area, all that, we can relate that with viscosity. I think I just repeated myself. Okay, so I'll say it again. So you can relate the velocity the force, the shear area, all that, you can relate that with viscosity. Okay, I feel like I'm repeating myself a lot, but okay, it's fine. So this is our formula. Shear stress is equal to our viscosity times du over dy. So this is like a differential, right? In certain cases, you might think that you might need to differentiate, but in certain cases, it's actually really easy. You don't need to differentiate at all. Actually, in most cases, you don't have to differentiate at all, because in this course, they don't really care if you can differentiate or integrate, right? They don't really care. They just want to see if you understand the concept. So they're not going to really make you differentiate something really, really hard, right? So, where was I? Yeah, so we're gonna be using this law of viscosity when we talk about our velocity distribution, right? So one other note, so I've introduced you guys to dynamic viscosity, which is like an approximate viscosity of a fluid. Kinematic viscosity is just our dynamic viscosity divided by our density. It's literally right in front of me. Yeah. In later stages of the course, you guys will see kinematic viscosity a lot more often, and you're gonna have to convert between kinematic viscosity and dynamic viscosity a lot. So that's why I've put it here a bit early, just to show you guys the relationship between kinematic viscosity and dynamic viscosity. Okay, let's talk about velocity distribution using our law of viscosity. So there's a few scenarios: scenario 1, 2, 3, and 4. Oh my god. Hey. So I'll pretty much explain what's going on. So scenario 1, we've got one moving plate and one fixed plate. So you can imagine that there's like two plates on top of each other, and within these plates there's some fluid moving through it, right? So top plate is moving, the bottom plate is just still, right? So what I've got here is something we call the velocity distribution. So it's pretty much the velocity of the fluid at certain heights of the plates. How do I explain this? So this is our height between the plates. We've called it y, and at certain heights above the fixed plate, there'll be different velocity distributions. Different velocities. Yeah, the fluid will be moving at different velocities. Yeah, that makes more sense. So pretty much, the velocity at the top plate, the moving plate, so our moving plate, the velocity is going to be the maximum, and the velocity of the fluid is actually going to be the same velocity that the plate is moving at. So let's say the plate is moving at a velocity u, the fluid at that point will also be moving at a velocity u. The way I like to think about it is, because if you go back to this over here, you can think of it as layers that stick together. You can think of that top layer sticking to the top plate, the moving plate, and therefore because it's stuck together, they'll be essentially moving at the same velocity. So at the top we have the maximum velocity of the fluid, and as you get lower and lower and lower, or closer and closer to the fixed plate, the velocity will eventually reach 0. This is what we call a non-slip condition, right? So the velocity at the fixed plate or the non-moving plate will be 0. Again, you can think about it in the same way. Because the fluid is stuck to that fixed plate and it's not moving, the velocity of the fluid will be 0. Alright. So using our law of viscosity on the right here, we know that tau, or shear stress, is equal to F over A, where A is our shear area, which is equal to our viscosity times, this is our du over dy. So du over dy is, if you think about it in math terms, it's literally just a gradient. So it's the gradient of our velocity distribution, or velocity function. So because this is a linear distribution, or it's a linear line, it's just a linear line, because it's a linear line, you can just use rise over run, right? So the amount that the velocity changes divided by the amount that the height changes. So you get this that's pretty much what du over dy means. So du over dy, you can think of it as amount u changes divided by the amount height changes. And we can tell that the amount that the velocity changes is u and 0. So it's just u minus 0, which is u. So that's our rise. And our run is pretty much just going to be the height. So it just changes. This is the change in height, essentially. Yeah. Or not much height. You can just think about it as a gap between the plates. Alright. Sometimes when you think about height, it might get a bit confusing in later scenarios. So just think about it as a gap between the fluid. Alright. Oh yeah, that's pretty much what it is. dy. So it's pretty much amount that the fluid, the height of the fluid. Don't worry about it, right? It's just a gap between the plates. Alright. Okay, so one moving plate and one fixed plate. So very, very similar. So we have a fixed plate at the bottom and we have a moving plate at the top. Again, the velocity at the top will be u, right? However, our velocity distribution is no longer a straight line. It's actually a curved line, right? So in this case, you are going to have to use differentiation. So we don't see this scenario a lot, right? We don't really see it a lot, so you're going to have to differentiate. That's why I've just put it in the formula just like that. Right? So they might give you some u function in terms of y. So u is a function of y, and yeah, you're gonna have to differentiate it. Alright, next, they're very, very similar. I still haven't covered what shear area is, but I want to cover it after. I want to cover it after this scenario. Okay, so one moving plate and two fixed plates. So, and it's a linear distribution as well. So we've got two fixed plates. So we've got fixed plate at the top and fixed plate at the bottom. So they're not moving. They're going to be our non-slip conditions. So u equals to, oh sorry, wait, wrong. Should be here and should be here. U equals to 0, u equals to 0. And then we've got one moving plate in the middle, right? And they've told us that it's moving with a velocity of 0.4 meters per second, right? So this velocity here, oh, you can't really see that. This velocity here is going to be 0.4 meters per second. So that's going to be our maximum velocity. Oh my god, you guys can't see that either. That's better. Okay, it's really, really blurry. Let me try to fix that up. Holy shit, that's even worse. Okay. I think it's just because of the background. Never mind. Yeah, so this red over here is just 0.4 meters per second. Now, someone has written a note, Henry. He written a note for the shear area. So before I go through that, I want to also go through this example. So yeah, you guys can, they've told us that it's a linear distribution, so it's a linear distribution here. One other thing is that you can assume that it's a linear if they don't tell you if it's a linear or non-linear distribution. In most cases, you can just assume that it's a linear distribution if the gap between the plates are very, very small. So for example, in this case, we got 2 millimeters. In some other cases, you might see 0.25 millimeters. Because it's so small, you can just assume that the velocity distribution is linear. Alright. Okay, next, fixed outer cylinder and moving inner cylinder. So this is from the workshop 1, question 3. So what we have over here is that we have a fixed outer cylinder, and so that's a hollow cylinder, and within this we've got a inner cylinder, like a solid block cylinder, right? And it's moving downwards with some velocity, we don't know. Right? It's got a weight force, we do know that. And one other thing that we know is that there's some sort of oil film on the side here that's causing it to slip downwards. Right? So the law of viscosity still holds. So tau is equal to F over A, which is equal to this times du over dy. Right. So what is the shear area in this case? So the way I like to define shear area is that it's the area that the moving object, no, it's the area of the moving, sorry, this makes no sense at all. Area that the moving object is in contact with the fluid. Okay, I guess that makes a bit more sense. So think about the moving object, right? So let's say a moving plate, a moving cylinder, a moving plate within two fixed plates, essentially. So in this case, this is our moving object, this is our moving object, this one is our moving object, and this one is our moving object, right? For each scenario. So think about the moving plate, and think about the area that is in contact with the fluid of the moving plate. So exclude the fixed plates, right? So don't even think about it. Just think about the moving plate. Think about how much of that moving object, right, is in contact with the fluid. So because there has to be some sort of shear action going on between the moving object and the fluid. So we only think about the moving object. So so how much of that moving object is in contact with the fluid? So in our first one, you can, if you like assume that it's like a rectangular plate like that. So I've drawn it in 3D. Just think it's going inwards into the page, right? And that the fluid is in contact with this whole area, just underneath the plate, right? So the fluid is attached to that part of the plate, right? So our shear area would be that whole rectangular area. I've got a better diagram here. So think about it like this. Our shear area is going to be that whole thing, right? And same thing with scenario number 2. The moving plate, the moving object is the moving plate, so we just take this whole area. In scenario number 3, however, the fluid is in contact on both sides of the plate, right? You can ignore the front and the sides because we don't know the velocity at that point, right? And the sides as well. You can just imagine that it's going infinitely, or not really infinitely actually. Just don't even worry about the sides. Just worry about the top and the bottom, where the maximum velocity is. That's how I like to think about it. Wherever the maximum velocity is acting. So the maximum velocity is acting at the top and the bottom of the plate, right? Same thing over here. The maximum velocity is only acting at the top of the plate. Maximum velocity acting at the top of the plate. So maximum velocity is acting at the top and bottom of the plate. So in that case, you're going to have to take the shear area. The shear area, is going to be the area of the top and the bottom plate. So it's going to be that rectangular area at the top and at the bottom, right? So it's going to be on both sides. For the cylinder, so the moving inner cylinder, the fluid is in contact with the outer area, the outer curved area of the inner cylinder. So this is our inner cylinder, and the fluid is in contact with this outer part here, right? So our shear area is going to just be that outer area, which is given by pi times d times h. Right? Pi times d times h. That's pretty much how you find shear area. And these are like the most common scenarios that you guys will see. Okay. That pretty much ends it for viscosity and velocity distribution. This is meant to be V, by the way. It's meant to be V, because they've already given us what V is. 50 millimeters per second. And also, one more thing I want to talk about this case is that the gap between the moving plate and the fixed plate is really, really small. Like, in fact, it's this gap is equal to 0.25 mm. Therefore, you can assume... Oh, come on. You can assume that it's linear. That's a linear distribution. Alright. Is it still recording? Okay, good. Next, let's talk about hydrostatics now. How long have we been recording for? 25 minutes. Oh, it's going to be pretty short, actually. Okay. Hydrostatics. Okay, hydrostatics. So pretty much hydrostatics, pretty much the study of pressure and the forces relating with fluids, right? So first of all, I'm going to talk about the pressure versus depth. So how does depth affect pressure? That's pretty much what we're talking about. So imagine that, okay, this is too much stuff right now. Let me take this out, no. Point this out, take this out. Okay, cool. No. I need that. Okay, get rid of this for now. Okay, beautiful. So, imagine 2 points under, like that's submerged. So 2 points under a fluid, well, within a fluid, point 1 and point 2. The height difference between these these 2 points, is given by h, right? So there's like a general formula. The pressure at point 2, which is a bit deeper than point 1, is equal to the pressure at point 1 plus the unit weight of that fluid. So this is our unit weight. This is the unit weight of that fluid multiplied by the height difference. So our height difference is just y2 minus y1. Or just h, because they've given us h like that. So the pressure at point 2 is equal to the pressure at point 1 plus the unit weight times h. There's also a proof for this over here. It's just a bit of math. You don't really need to worry about it. But that's our general formula for calculating pressure. So this is only true if the point 2 is below point 1, right? So because you can see that pressure at point 1, so just based off the formula, pressure at point 2 is going to be higher than the pressure at point 1, right? Because you're adding something to pressure at point 1. That sort of makes sense, right? You can also think about it in another way, that the deeper you go into an ocean, the more pressure it's going to be. You can think about the Ocean Gate submarine that imploded a few years ago. So when it lost control, it kept getting deeper and deeper and deeper. So the pressure that the water was exerting onto the submarine is getting larger and larger and larger as it got deeper and deeper, right? So eventually it couldn't take it anymore and it imploded. Oh no, I think that's what happened, right? But it's true that the deeper you go, the more pressure you're going to experience in a fluid, right? Yeah, that's fine. So exactly, I'm going to quickly talk about the measurement of pressures. There's something called simple measurement. So this is using piezometers and simple manometers, and there's also something called using differential manometers. Okay, I should probably write it as differential manometers. Manometers. Okay. So when it comes to simple calculations, so using either a piezometer or a simple manometer, there's always going to be one pipe end and one atmospheric end. So pipe end meaning the piezometer is connected to a pipe, and within that pipe there's going to be some sort of pressure within the pipe, and an atmospheric end, which means that the other end of the pipe is going to be connected to the atmosphere, or you can just think of it as the pressure is going to be 0, right? Even though there is some atmospheric pressure, when it comes to like analyzing it with piezometers, you can just take it as 0. So in a piezometer, so this is our pipe cross section. So we're just taking a look at it from the side. So imagine this V-can. We're taking a look at it from this side, right? And this is our piezometer just getting connected like this, right? So this is the pipe end that's analyzing the pressure in the pipe, right? and this is the atmospheric end, which is in contact with the atmosphere. Right. For a simple manometer, it's a bit different. There's actually more than one fluid that's acting, that's within the pipe, the manometer, right? So again, we've got a pipe cross section or a pipe end, right? Then there's going to be one fluid, and then another fluid, and then after that another fluid. It's going to be connected to the atmosphere. I don't know why they use more than one fluid. I think it makes calculations a bit more accurate. I don't know though. I just know how to calculate the pressures. That's for sure I do. Differential manometers. Okay, so that was simple. The only difference between simple and differential is that instead of having an atmospheric end, it's actually got two pipe ends. So it's going to be one pipe connected to another pipe. So these are the two pipes, right? And there's going to be some pipes. No, there's going to be some tubes that are going to be connected to each other. No. Yeah. So there's going to be a tube connecting from this one to this one somehow. And within those, there's going to be certain fluids again. So these are our two pipes, pipe cross sections. In our first part, in our tube, the first part is consisted of fluid 1. Then it's got a different fluid here, and then it's got another fluid which finally connects to pipe number, finally connects to part B. Pipe B, right? So, and to find the pressure at pipe B, alright, to find the pressure at B, you're going to have to first of all be given the pressure at A, and second of all, relate the height and unit weight of the fluid again, like we did earlier, over here, to formulate this equation over here. So you might be thinking, how the hell did we get to this equation, right? So we're trying to find the pressure at point B given the pressure at point A. Right. So based off this diagram, the only thing that we know is that the fluid has a unit weight of gamma 1, fluid 2 has a unit weight of gamma F, fluid 3 has a unit weight of gamma 3, right? This is what's given in the diagram, right? You know what, I'll change this to 2 to make it a bit more easier to understand. So 2, and then therefore this will be 2 as well. 2. Okay. So how the hell do we get to this equation here? So I've written up some rules. So you start from one point. For example, let's start from point A. Then you're going to be taking a look at the fluid. So let's say we start at point A. So whenever you're looking at the pipes, you always start from the middle of the pipe. So when you go up, the pressure will decrease. That makes sense. We talked about it earlier here. When you go down, the pressure will increase, but when you go up, the pressure will decrease. So when you go down, pressure will increase. When you go up, it will decrease. And there's like a general formula, right? I don't know what this is meant to be. Pressure down is equal to pressure up plus... No. Like this. Okay, so what's going on here is that when you start from point A, when you go, let's say... So what this really means, the pressure increase and decrease, the only thing that affects is our delta H here. Whenever you increase, you will have a plus, but whenever you decrease, it will become a minus. Alright, so I like to have it as a plus minus. I'll say plus is this, minus is this, right? Plus minus. And the formula for it we know is the unit weight of the fluid times the height difference. Right? So pressure decrease, you take it as a minus. Pressure increase, you take it as a plus. And As you analyze more fluids, you add more terms. You keep adding more terms for each fluid. So let's say this is for fluid 1. If you want to do another fluid number 2 times delta H, blah blah blah. Right, so this is pretty much what I've done with this one over here. So pressure at point A. So we start at pressure at A. Then we're trying to take a look at fluid number 1. So this is the whole of fluid number 1. What we're trying to see is where that fluid ends. So we know that it ends over here. So all we need to do, we know what the unit weight of the fluid is. It's gamma 1. What we're going to have to do is we're going to have to find the height difference between point A and the ending of that fluid. So this is our height difference here, ZA, between here and here. Alright. So pretty much the way I'll go through that later. Next, let's analyze fluid number 2. By the way, it's negative because from point A you're going up to our new point over here, A dash. Right. So what we've analyzed is we've gone all around the pipe and we've ended here. So the height difference between here and here is ZA. Done. Okay, so that's the first part. Next is going to be fluid number 2 that has unit weight gamma 2. Right. So again, it starts over here. Where does it end? Up here. So again, our height difference, which is Y, is positive because it's going up. We're going up, right? So the pressure again is going to be a decrease. And also the general formula when you're taking a look at each fluid individually is going to be the pressure of that fluid is going to be equal to the unit weight of that fluid times height, or times delta height, change in height. Yep, that's better. So you're gonna have to use this formula for each fluid that you're analyzing. So I've done it for the first fluid here. Oh, sorry, over here. Right. I've done that the unit weight is gamma 1, height difference is at A, and I've taken it as a minus because we're going up. Next, unit weight is gamma 2, height difference is Y, and I've taken it as a negative because we're going up. Right. Next, let's take a look at our last fluid number 3. So fluid number 3 starts here and it ends at point B. Right. Again, because it's a pipe, we take the middle of the pipe. In this case, we know that our unit weight is gamma 3, but the height difference, ZB, is negative. ZB is negative. It's not really negative, it's just we're going downwards. So the pressure change, so these are all pressure changes, by the way. So I should probably denote this as pressure change. So at certain points of the pipes, of the tubes, the pressure changes by this much. Right? Oh yeah, that's a really good way to think about it. Oh, wow. Okay, I'm going to use that for my next class. Okay, I'll quickly explain what I found out. But again, fluid number 3 has unit weight gamma 3 and a height difference of ZB. And because it's going downwards, our pressure change is going to be positive. Okay, so the way you can pretty much do this easily, take a look at the diagram. Start at point A. So let me get rid of this. Start at point A. Go around, pretty much just follow the diagram. Follow the tube. So you're starting here. First fluid ends here, right? So what's the pressure change? It's going to be this. Right? Again, you continue. Fluid number 2 starts here and ends here. What's the pressure change? It's going to be this. Last fluid starts here, ends all the way here. What's the pressure change? It's going to be this. Then you combine all the pressure changes and the initial pressure, and you finally get your pressure at point B. So you start at point A, and then you have when you include all the pressure changes, you have your pressure at point B. Okay? So it might be a bit confusing, so I'll explain it with a diagram here. With a example here. So we have water, point A. We've got an oil. Yeah, we've got a red oil with specific gravity 0.827. And we've got mercury over here. So they've given us the pressure difference between point A and point B, PB minus PA. They've given us the unit weight of water. So in this case, we can't assume it's 9,810 because they've given it to us. And they've given us the unit weight of mercury. What we have to do is that we have to find the point H. So I'm gonna work through this with you guys. So let's start at point A. So the pressure at A, there's gonna be some sort of pressure at point B. So I'm gonna start at point A. Pressure at A. Then what we're gonna have to do is that. Oh, I lucky forgot. Okay, so this fluid number 1 is water, right? So we take the height difference, which they've already given us to be H. We multiply that by the unit weight of water. So unit weight of water times H. And because H is going, so the point that the water ends is above point A, because the height difference is positive, we have to take it as in minus. So minus. Next, we're gonna have to take a look at the oil. Right. Alright, first thing I should have done probably is converted this SG into a unit weight. So unit weight of the oil, which is our fluid, divided by the unit weight of water. So they've given us that 0.827 is equal to unit weight of oil divided by 9790. Therefore the unit weight of oil is going to be 9790 times 0.827. 8096.33 newtons per meter cubed. So now we can actually analyze the oil now. So this oil, it starts off, over here, this purple mark, and it ends up here. So the height difference is positive again, and it's 18 centimeters. So it's going to be, because it's going up, minus the unit weight of our oil times 18 centimeters, which is 0.18 meters. Okay, next we're going to have to take a look at the mercury, our final liquid. Our final fluid. Alright, so mercury starts off at our purple point here, and it ends at the point B here. So the height difference is going to be negative, so it's going to be a positive pressure change. And it's going to be 18 plus H plus 35. So 18 no, it's 0.18, sorry. And this is equal to because we've reached point B, we can finally say that this is equal to the pressure at point B. So we know what PB minus PA is, so I'm gonna take this to this side. PB minus PA. This is equal to 98 kPa. 98 kPa. That's equal to 98,000 pascals. We have to convert it because the units for pascals. So for pascals, the units are newtons per meter squared. Okay, so let's calculate this finally. Plug in all our numbers. 9790, yep, times h minus 8096.33 times 0.18 plus 1331 times 0.4553 plus h, which is equal to 98000. Let me get my calculator out. Alrighty, so 8096.33 18. So you get h is equal to 23.4 centimeters. I'm pretty sure. 23.4. Wait, let me check my answers. Yeah, 23 centimeters. Yeah, close enough. Right, 23.4 centimeters. Right. Okay, next. That's the first part of hydrostatics, pressure and pressure change. The next part of hydrostatics is forces on a submerged body. So what we have here is a floodgate. So this is a floodgate or a submerged body. So this is like more so in like a real case scenario. There's like a floodgate, and on one side of the floodgate there's water. So there's that water side. And obviously this water is going to be pushing on the floodgate. So it's going to exert some sort of pressure. Alright? And what I've got here in red is our pressure distribution. It's similar to distributed loads from ENGG2500. Right? So there's going to be some sort of equivalent force because of the pressure distribution. And that is what we call a hydrostatic force. The force exerted by the water on the gate. Right? So, before I actually do continue, I want to talk about this small sign over here. This is something they don't go over in the lectures, but it's pretty much just a water table. So the surface is pretty much, when you see that triangle with the two lines at the bottom, it's pretty much just going to denote the top of the surface of the water. Is that right? Yeah. So it's the surface of the water. And so it's pretty much the atmosphere. So PATM. And that's why if you take a look at the pressure distribution, it's going to be 0 at this point. So this is when it's 0. So P equals 0. And then as you move further and further along, the pressure will reach a maximum of rho g times h. Or, as you guys know, that rho g is just equal to a gamma times h. Alright. So, if we take a look at the hydrostatic force, it's given by, what the hell's going on? It's pretty much just given by the area of the triangle. Alright, so the area of the triangle is going to be our first force per unit length. Right, so per meter length. Right, where we have the area of the triangle being half times base, which is rho gh times our height. So this is going to be our height. So it's given by newtons per meter into the page. So that's if we don't have the width of the actual gate itself. So this is just a 2D view of it, right? We don't know what the width of the gate is, so that width of the gate, That's going to be the pressure distribution in 3D, which I've actually drawn over here. So given that the width of the gate is this, the pressure distribution will actually look something like this in 3D. So given that the width B, so let me get rid of this. Given width B into the page, right? The force, the hydrostatic force is given by this. So this is the main formula that you guys are going to be using for this, right? The force into the hydrostatic force, right? Where the area is the area of the gate, which is height times base. Right? So this is scenario 1 of vertical plane surfaces. Alright. Scenario 2 is when you have like a trapezium distribution. The reason for this is because the gate doesn't extend the entire way up to the surface. So in this case, the gate does extend the entire way up to the surface. In this case, it doesn't. Right? So again, this might look a bit terrifying to look at, right? But this is how they give it to you in the exams. So this is what it looks like. This is a better, more an actual way that you guys will see in an exam. So there's 3 things they give to you. They give you the side view of the gate, right, with the water table at the top. Then they give you a cross section. So they give you a cross section, and then they give you a pressure distribution. So these are all this is like all the same thing that you're looking at. So it's not different things. So even though this is the gate, this is just looking at the cross section of the gate, right? This is also the gate, but from a side view, this is just looking at the pressure distribution of the gate. All right, so don't get confused. They are the same thing, but they're not the same thing at the same time, right? So there's a few formulas that are actually given in the lecture. So this one is our general formula. So that's if you want to do some integration, but in most cases you don't have to. This is for a trapezoid. So something like this, you can just straight up use this formula and you'll get it correct. And this is another general formula that I like to always use. This formula has never failed me. A is the area of the gate. HC is the height of the centroid. So the centroid of the gate in this case is going to be the middle. If you have different shapes, like if you have a triangle, you're going to have to find the centroid of that triangle and then find the height up from the surface. So in this case we have HC being something like that. Right, so HC, height to the centroid from the surface. If it was a circle, circle's pretty easy, centroid's in the middle. Semicircle, centroid's a bit different. Right, so you're going to have to find the centroid first of the shape and then find the height from the surface to that centroid. And then you can use it straight up, use this formula straight up. Alright. So there's 2 things we actually have to calculate for something like this: the hydrostatic force and the point of application. The point of application for this case is really, really simple because this is a triangle. So we know that will be 2/3 from the lower end, or the smaller end, or 1/3 from the bigger end, right? However, for something like this, it's a bit harder to tell, right? So this is a formula that you guys don't have to derive. They do derive in the lecture, but you can just straight up use this formula. It's actually on the formula sheet as well, which is really, really good. So the point of application, YP, is equal to the second moment of inertia, second moment of area, sorry, it's a, what's it called? The moment of inertia of the gate around the centroid. That's why the centroid is there. Oh, okay, sorry, I've got it wrong. So what the C actually denotes is the moment of inertia of the gate, right? So if you were to just see this without the C, it would be the moment of area of something else, but it's way too hard to calculate. So what you're going to have to find the moment of inertia separately. So find the moment of inertia of this gate, right? So for a rectangle, it's BD cubed over 12. Then you want to find HC and A, pretty easy to do. And then finally, you're going to add this to HC. And that will give you the point of application, right? So don't get too confused with this. Just take a look at the shape of the gate and find the moment of inertia. Second moment of area. Okay, I forgot what it's called, but something like that. Just find IXS, just use the formula, right? Okay, so that was taking a look at vertical plane surfaces. Now, let's take a look at inclined surfaces. So pretty much, this is our water table. This is our a gate in the green, right? And I've denoted the centroid of the gate. So HC is given by that. YC is pretty much the angled height to the centroid. So it's a bit different. The reason it's important because you actually have to use it when finding HC. So unless they give you HC, you're going to have to find it yourself. Right? So in most cases, they'll give you what YC is, or they'll give you this height, this Y height, right? And you're gonna have to find HC from that. So HC usually they don't give it to you. If they do give it to you, bless. If not, you're gonna have to find it yourself. So and the formula is the same, exactly the same. The only difference is HC. However, the point of application gets a bit stupid. You're gonna have to find YP and XP. So sort of like a Cartesian coordinate, XP and YP. Their formulas are very, very similar. Very, very similar. So the only difference is the green and the blue. So for YP, you've got to add it to YC. For XP, you've got to add it to XC. For YP, you take a look at the second moment of inertia. For XP, you take a look at the polar moment of inertia. So IXY, rather than IXX or IYY, you take a look at IXY. So IXY for vertical, for rectangular surfaces is 0. You'll learn that in ENGG2500. So for rectangles equals 0. I think for circles, perfectly circular circles, it's equal to 0 as well. Mainly because it's symmetrical. That's why. But for triangles and some other shapes, it differs, right? In this course, you won't get anything too bad of a shape. You'll probably get a circle. That'll probably be the hardest one, right? I've never seen anything harder than a circle. Okay, so that's forces on an inclined surface. Okay, next is curved surfaces, but I'm not going to bother going through it because it's honestly really, really difficult. Okay, continuity. So moving on to our new topic. So that's pretty much hydrostatics done. We're going to move on to continuity now. What's the time looking like? Okay, beautiful. So I'm going to introduce you guys to fluxes. So there's three types of fluxes: volume flux, mass flux, and momentum flux. So each of these have a different unit, obviously. And what the volume flux is that you're taking a look at the amount of volume of the fluid that's going through a pipe per second, right? So imagine you have a pipe, and what you're trying to see, what the flux is the amount of fluid going through the pipe per second, right? That's pretty much what flux are. Just the amount of fluid going through a pipe per second. But it varies to do with volume, mass, and momentum. Momentum you don't really look at too much, so I'm not going to bother going into it. We mainly look at volume flux and mass flux, right? You guys can take a look at the derivation of the units. I'm not going to explain that. I'm just going to show you guys how to use one of the formulas, right? I'm not going to bother showing you guys both, just one of them is fine. So calculating fluxes. So the average velocity that First, another thing, this U over here is the average velocity of the fluid. A is going to be our cross-sectional area of the pipe, right? So average velocity the fluid travels through the pipe is 2 meters per second. Find Q. So they've also given us the diameter of the pipe, thankfully. So you can actually just find the cross-sectional area. So if this is D, our cross-sectional area A is given by pi d squared on 4, or you can find the radius and use pi r squared. Right, so I've used pi d squared on 4, so it's A times U, cross-sectional area, and our average velocity. So subbing in D equals to 0.5 and U equals to 2, you get this as our flux. So it's a value, it's a numeric value, our flux. Okay, 0.393 meter cubed per second. Okay. Now I'm gonna quickly touch on control volumes. Control volumes are pretty much a certain I don't know what they are. Okay, I think they're just the volumes that you part of the volume that you analyze. Because in some cases they can be finite or infinite. Finite cases are pretty easy. You just take a look at the finite area. For infinite areas, you can't analyze the whole thing. That's literally impossible. Alright, so control volume does what it does is that you kind of set boundaries, right, and you're analyzing that certain part of your system, right? But there must be boundaries, so controlled surfaces, but the boundaries can be fixed or deformable. Deformable meaning, so an example of fixed, first of all, is like two fixed pipes, and there's going to be water within here traveling like that. So our control volume is just going to be something like this, right? And it's cut off by these two. The deformable ones, an example of that is the open surface. So if we're taking a look at something like this, a weir, right? So we've got water flowing this way, like that, right? So this is going to be our boundary layer over here. So the boundary here, so not the boundary layer, the controlled surface, right? So this controlled surface over here is deformable, right? Because it's exposed to the open air. Whereas over here, it's fixed. And over here, it's also fixed. So what control volumes really are, it's just part of the system that you're analyzing. So, I guess it varies from example to example. So obviously there can be like a pipe contraction. So a pipe with a larger diameter contracts into a pipe with a smaller diameter, right? So this is going to be our control volume. So the part of the system that we're analyzing, right? And there are certain rules about it. So boundaries can be fixed and deformable. They may only contain fluid, and the fluids have to be incompressible. So for ENGG2500, we don't look at compressible fluids. So what it means by incompressible means our density is constant. The density doesn't change. Because if you think about it, compressible means that the volume can change. It can get compressed, right? So the volume for density, which is mass of volume, the mass obviously never changes. Mass is always a constant. Volume, however, can change. If it's incompressible, it doesn't change, and therefore our density stays constant. But if it is compressible, this can change, so it can vary, and therefore this can vary as well. But those kind of questions are way too difficult for us, so we don't really look at them. And that's why we have controlled volumes, right? Because this volume that we're looking at does not change. In real life scenarios, it might change, like this water might like escape, blah blah. We don't worry about that. We always assume this controlled volume. Okay. Next, bucket hydraulics. So I'm going to introduce you guys to some continuity equations. So I've got something called the Mama formula and the Big Mama formula. So these are true for volume fluxes. So Um, the sum of all volume fluxes going into a system must equal to the sum of fluxes going out of the system. Alright, so that's what we call the mama formula. The big mama formula is that the difference in the change in flux, right? So the amount going in minus the amount going out is equal to the dV on dt, right? And I've written a note here that dV on dt is equal to A times dH on dt. A is our plane area. So if you think about a bowl of water, the plane area is just the area of exposed fluid at the top, right? So this also relates to our volume dV on dt, right? So I'll show you guys this in like an example. Consider a pipe junction. Over here we've got some volume flux going in, some volume flux going in, and some volume flux going out here. Right? So we know that the amount going in has to be the amount equal out. That sort of makes sense as well, that the amount going in here and in here will like combine together and will equal to the amount going out. Therefore, if we're subbing into this equation, we can say that Q1 plus Q2 is equal to Q3. Right? And that's pretty much how we use that equation. And the only difference between the mama formula and the big mama formula is for mama dV on dt is equal to 0. So the amount of fluid within the system doesn't actually change. That's what it means. So dV on dt is the amount of fluid changing over time. The amount of fluid does not change when it comes to the mama formula. Right? And why this topic is called bucket hydraulics is mainly to do with this one over here. So in a bucket, if you imagine a bucket, so a bucket, and it's got like a small leak over here. So a small leak, water's flowing out like that, and there's some water going in as well. These are some rules that we have. So if the amount of going in is equal to the amount of going out, so there's no change in volume, so this volume will stay constant like this the whole time. It will stay constant like this the whole time. So dV on dt is equal to 0. However, if the amount going in is greater than the amount going out, that means the bucket will fill up, or our dV on dt is greater than 0. So if you think about it, if the rate of this going in is a lot, however this is very, very small, not much comes out but a lot goes in, it's pretty much like you're filling up a bucket with like a small leak at the bottom. So eventually this will fill up. However, if the amount going out is greater than the amount going in, so if you're losing water at a greater rate, so there's only a bit going in, but there's a lot going out, that means this volume will eventually decrease over time. I'm not sure if there's any better way to explain this, but yeah, when it comes to continuity, you can, or bucket hydraulics, you can think about this bucket scenario. So the amount going in, if it's got the amount of water flowing in, if it's greater than the amount going out, then the bucket will fill up. In the opposite case, if the amount flowing out is greater than the amount flowing in, then the bucket will drain, or it will decrease in volume. Right. Hopefully that makes sense. And these are the type of continuity problems that we take a look at in this course. Right. most of these will be covered in the lectures anyway, so don't worry too much. Okay. Bernoulli's equation. So I'm going to quickly move on to energy. I'm just going to introduce you guys to Bernoulli's equation. It's not too deep. No, it is actually pretty deep, because you're going to have to use it throughout the rest of the course, right? So there's actually 3 parts to this equation. So pressure head, velocity head, and elevation head, right? And along a streamline, which you will be introduced to in a lecture, it will always stay constant. So this equation will always stay constant. So Bernoulli equation, what it is pretty much combines energy, so different types of energy. So gravitational potential energy, kinetic energy, and one other sort of energy. I forgot what it's called, right? Combines them together and pretty much combine them together. That's pretty much all it is. And I don't know how to explain it, to be honest. But pretty much this one comes from the gravitational potential energy. This one comes from kinetic energy. This one comes from the pressure energy, or like some sort of energy, right? Hydrostatic pressure or whatever, right? So we call these heads, but what head actually is pretty much just a length, right? So what this equation has done is that it's converted energy into some sort of measure of length, right? So the whole equation, we call it the total head. So if we combine all the heads together, it will give us some sort of length. So this is more to do with pipe flow, which you guys will see. Let me take a look if I can show you guys an example. So this is the gravitational potential energy. Oh yeah, sorry. The last part, the pressure head, is just the work done by pressure. So it's the work done by pressure. This is the kinetic energy part. Yeah. So it's more so in this like pipes. You can, whenever you're analyzing pipe flow, or like some sort of what is it, pressure within a pipe, like piezometer that we have over here, the height of like that the water reaches, or like the fluid reaches within the piezometer, can actually tell us something about the pressure and energy. So that's what the Bernoulli equation does. So something over here. So we've got a piezometer and a pitot tube, right? So the difference between height of this and this, so this part and this part, is given by the velocity head. The pressure head is given by the height difference here. And the total head is everything combined together, right? So they've pretty much brought energies together and converted it into like heights, and like what the difference in height, what it can like pretty much do. I don't know, I'm just yapping right now, but you'll learn more about it later on, because there is a lot more, right? This is an introduction to like the equation itself. I haven't gone through any examples, but I don't really have time to either. So one last thing I'm going to introduce you guys to is called the Reynolds number. No, I want to keep that. So Reynolds number is a dimensionless unit, right? So non-dimensional number used to predict if a flow is either turbulent or laminar. Laminar flow is like a really nice type of flow. Turbulent flow is a chaotic flow, right? Laminar is smooth, nice, and we can find what the Reynolds number for a certain fluid, right? And for a certain flow, and we can predict if it's laminar or turbulent. So we've got density, average velocity, pipe diameter, and dynamic viscosity. So if you guys remember, I introduced you guys to kinematic viscosity earlier. So you can also relate this to kinematic viscosity. So Reynolds number is equal to U times L over kinematic viscosity. same thing. You can use whatever you want. Doesn't really matter. Okay, so if our Reynolds number is greater than 4,000, then we have something called turbulent flow. If it's less than 2,000, then we have something called laminar flow. If it falls within 2,000 and 4,000, then we have something called transitional flow, which we don't actually care about too much in this course, mainly because in real life they actually haven't like figured out what transitional flow really is, and like any calculation to do with transitional flow. It's really difficult. So mainly we care about turbulent flow and laminar flow. And questions, it will most definitely be laminar flow or turbulent flow. If you get transitional flow, then GG, unlucky. And I've also pretty much given like a bit of description about laminar flow and turbulent flow, which you guys can read in your own time. For now, these are some dimensions. This you guys should have already looked at in your first lecture, or you guys will take a look at it again in week 7 or 8. So these are parameters and variables, the symbols for them, and the units for them. So it's pretty good to take a look at the units as well and get used to them, because in this course units matter a lot, and you guys will see in dimension analysis that you guys are actually going to be analyzing units rather than analyzing fluids. You guys are going to be analyzing units, so that's why it's really mind-numbing. But yeah, that's it. Thank you for watching. Hopefully this was helpful. I'll also upload my drive for like all my notes and stuff into the description of this video. Alright, thank you guys, bye bye.